Here we're going to look at a BJT being used as a switch. Here's the circuit here where we have an NPN. Again, this is the emitter, and you can see the emitter is grounded, and then we get a base resistor connected between the base of the BJT and VN. And then here at the collector is connected to where the output voltage is taken. Okay, here V0 is the output voltage. Here's a supply voltage VCC, and you can see there's a resistor, the collector resistor RC, between this source and the collector of the resistor. Now, I've repeated the current voltage relationship at the collector side of the BJT. Remember that these are constant base current curves, and we already talked about how when the BJT is used as an amplifier, we operate it in this region here that's called the active region, where beta is fairly constant, and also for all practical purposes the optimum beta. Now what you'll see is that when the BJT is used as a switch, we're either operating near the horizontal axis where both the base current and collector current are ideally zero, or in actuality very small, and that's called the cutoff region, or the transistor is being operated along the vertical where we have a small VCE, ideally zero, and some amount of collector current. And you'll also see that in this region you do have current gain, but it's not the optimum current gain. Now, very important, there's two conditions that must be satisfied for the BJT to be operated as a switch. The first is that this input voltage can only be one of two values. One of the VN values reverse biases the diode that's between the base and the emitter of the BJT, and typically the value that's used for VN is 0 volts for this. Alright, so any value that reverse biases this base to emitter can be used, but most often we just use 0 volts. And then the other value of VN has to be a value that forward biases this diode between the base and the emitter. And in our examples we're going to use a value of 5 volts. Okay, but in other type of BJT switch circuits, this positive voltage value here that gives the forward bias case, can be some other voltage. Okay, the second condition is that when Vn is the forward bias value, this resistor RB is selected such that it makes the voltage from collector to emitter of the BJT ideally 0 volts. Okay, this is ideal. Okay, and most of the analysis that we'll do here will be an ideal analysis. So for a non-major class like this, I don't go into actually showing you how to get the specific value of RB. That's covered in the text if you're interested. It involves what's called a load line analysis. But in a non-major class like this, what I do expect you to know, based on previous discussion, is that you should understand that the value of this resistor in the base region affects what the voltage from the collector to emitter is over here on the output side of this circuit, right? And that's because we talked about how a BJT is a current control device where you're controlling a current over at the collector side with a current on the base side. So by picking an RB value, I change, or I have the ability to change what the base current is, and if I can change my base current, well, that will cause a corresponding change in my collector current, and that will affect this voltage collector to emitter, because the amount of current through this resistor determines the voltage drop across that resistor, and VCC here is a fixed amount. So by varying this drop across the collector resistor, I'm also affecting this collector to emitter voltage. Alright, so as long as we have these conditions, two conditions, we're going to have a BJT acting as a switch. So let's go ahead and do the analysis. And this is a general analysis. The next video will be a specific example of a BJT switch. So let's start with one of the Vn values. Let's say that Vn is 0 volts. And one way that could be obtained is just by putting a wire, a short, from this node here right to ground. So if we put a short like this, that would make Vn equal to 0. Well, if Vn is equal to 0, this diode, this PN junction between the base and emitter, has to be reverse bias, because we would just have equal potential on both sides, and ideally that base to emitter would be completely off, and it would be reverse bias. And if that PN junction's reverse bias, well, there's not going to be any current flowing in the base, right? Because ideally this diode, this PN junction between the base and the emitter, would act like an open, and that would make our base current equal to 0 amps, meaning that there's no free charges getting into the base region of the BJT. Well, if I don't have any base current, then I don't have any collector current, right? Because on the characteristic here, the IV characteristic, I would be right on, ideally I would be right on this horizontal axis here where the base current is 0, so my collector current would also be 0. Okay, and if I have 0 current at my collector, that means the voltage drop across this resistor RC, okay, VRC, would be 0, right, since there's no current flowing through it. And that means V out, okay, and V out, again, that's this node where the collector of the transistor is connected to. So V out with respect to ground is the same as VCE. Well, that would just be equal to VCC since there's 0 volts dropped across RC. Okay, so ideally this is what we have. Now, in actuality, this base emitter that's reverse bias, just like a reverse bias actual diode, in actuality you have a little bit of current. So, in actuality there would be a little bit of collector current, so therefore there'd be a small drop across this resistor RC, and instead of VCE equal to the source voltage, it would be a little less. So you see, when Vn is equal to 0, the BJT is being operated right close to, ideally it's right on the horizontal, but in actuality it's real close to the horizontal axis, meaning that both the base current and the collector current are very small. Ideally 0, but in actuality very small. And this is called the cutoff region. Okay, so when Vn is equal to 0, the BJT is being operated in the cutoff region. Okay, and likewise, if you think about this, if you just look at the collector to emitter of the BJT, there's 0 current, okay, because the collector current is 0, and yet there's a voltage across, and in fact ideally that voltage is the source amount. So the collector to emitter, and this is really a key point here, that the collector to emitter of the BJT has the same voltage current relationship as an open does, because just like an open has 0 current for some voltage across it, any amount of voltage, well here the BJT is going to have 0 current for any VCC that's across it. So we say that the BJT from collector to emitter, when Vn is equal to 0, is acting like an open. So it's like a switch that's off. Alright, well now let's look at when Vn is the other possible value, enough voltage to forward bias the base to emitter. And in this example we'll use 5 volts, but it could be any voltage that forward biases that base to emitter. Okay, well, base to emitter is going to be forward bias. Alright, and just to make the diagram here agree with this case, remember this short being here was the case of Vn equal to 0. But now, one way that we could make Vn equal to 5 volts is here. 5 volts is just to put a 5 volt source. Okay, so Vn 5 volts. So you see now a base current's going to flow. Okay, you're going to get a base current flowing. and that base current would just be Vin minus the drop across the forward bias diode. So if it's silicon, it'd be 0.6, but since we're doing everything in variables here, we'll put VBE. But again, if that's silicon, if it's a silicon transistor, VBE would just be 0.6 volts, and then divided by RB. Okay, so that's your base current. Now, if there's a base current flowing, you will get a collector current. Now, this is a key point here, that if you remember back when we talked about a BJT amplifier, well, collector current was just beta spec times IB. Okay, this was when we were doing the amplifier analysis. Well, you cannot use this equation for a BJT switch, and the reason being, as you'll see in a moment, when the BJT switch is on, we're over in this region here where the curves dip. Okay, we're along this horizontal axis, or excuse me, this vertical axis. So we're not in the active region, and you see this equation's only valid in the active region. So the way that you obtain the collector current when you have a BJT switch is you just do a KVL around the collector loop. And here the KVL is real simple because you only have a source and a resistor. Now this is where the second condition comes into play, that remember, when Vn is the forward bias value, we select RB such that VCE is equal to 0. So you see the collector essentially is tied right to ground when Vn is the forward bias value. So all we have here when we do the KVL and solve for IC is that we just have IC is equal to the source voltage VCC divided by RC. And what we'll see when we do a specific example in the next video is that IC can be appreciably bigger than IB. Now it can't be equal to the optimum amount, based on beta spec, because we're not in the active region. But you can still have current gain with a transistor, with a BJT, even though it's not in the active region. It just won't be the optimum amount. And again, we'll see that with numbers in a specific example coming up in the next video. Alright, but just to continue on here, as we said earlier, and we make this happen again with the selection of the resistor, the base resistor RB, is that VCE, okay, which again is the same as V out, well, VCE is made to equal 0 volts. So you see, when Vn is the forward bias amount, ideally your VCE is 0. Now in actuality, it will be close to 0, maybe like a couple tenths of a volt. So you see, really what you have here is you're operating the BJT right in this region along the vertical axis, and that's called the saturation region. Saturation is an N here. Okay, I'll write it down here. Okay, so when Vn is equal to 0, you're in the cutoff. When Vn is the forward bias amount, say 5 volts, like in this example, you're in saturation. Okay, so you see here, switch off, here, switch on. And then the last thing is that if you look at just at the collector to emitter again, this voltage current relationship, well look, VCE is 0 volts, and yet there's a current. Okay, because this IC, when it flows from VCC through RC, then it goes collector to emitter to ground. See, that's your path for IC. So you have an amount of current flowing from collector to emitter, okay, that's this VCC divided by RC, and yet there's 0 volts across the collector to emitter. Well, that's the same VI relationship as a short. So you see, we say that the collector to emitter of the BJT is acting like a short, okay, when you have the forward bias Vn amount. Alright, well, like I said, this was a general analysis to show how the BJT is being, or how it functions as a switch. In the next video, we'll do a specific example.